Hi everyone. So welcome to this first webinar that is co-organized by GENCI, CEA and Quandela. So the context for this whole initiative is the acquisition of the Lucy photonic quantum computer by EuroHPC joint undertaking. This quantum computer will be provided by Quandela and Atocube Systems. And it will soon be delivered at CEA TGCC and connected to the Joliot-Curie supercomputer. And it will then be available to both French and European users for free for open research. Ahead of the deployment of the Lucy quantum computer, GENCI, CEA, and EuroHPC have decided to provide a remote access to similar architectures through the Quandela Cloud. Again, free of charge for open research communities, both in France and Europe. Today's webinar aims at showing the procedure to request access to the Quandela Cloud via the eDiary portal that will be shown today. And this part of the webinar will be handled by my colleague Félix Givois, who is Quantum Computing Projects Engineer at GENCI. And the second part of the webinar will be devoted to the presentation of the Perceval environment and how to program a first algorithm and submit it to the Quandela Cloud. And this part will be presented by Samuel Horsch, who is Quantum Applications Architect at Quandela.
So thank you, Sabine. Thank you very much for this nice presentation. So I will start the presentation to present a bit of context on this acquisition and this access to the quantum system by presenting the HQI initiative. So what is the French Hybrid HPC Quantum Initiative? So HQI in short. It's two things. It's first a hybrid HPC quantum production platform that is aiming to acquire and install and deploy quantum system in an HPC center. But it's also an industrial and academic research program that aims to first develop the software stacks that will be used to connect the supercomputing platform to the different quantum computers, but also try to understand and develop some use cases that on this hybrid ecosystem. Moreover, there will also be some community and end user support so that we can disseminate and teach to people how to use this type of different hybrid devices. So what we are trying to develop with this with the HQI initiative is a national hybrid platform. So in the center, you will have this supercomputing center that is held by the CEA and is called the TGCC. So in French, it's a très grand centre de calcul, which is basically meaning the big computational center. In the center, you will find a supercomputer called Joliot-Curie that will be replaced by the end of 2026 by an exaflop HPC system that will be acquired through the EuroHPC joint undertaking and will allow for European access and international collaborations. Around that, you will have some stuff that will revolve. So first is the most intuitive thing that you can do by trying to create a hybrid platform is trying to install emulation capabilities. So emulation are classical computing algorithms that are trying to replicate the behavior of a quantum system. So that the first thing that we gave available to our users. So there was first quantum agnostic algorithm, so that don't really rely on a specific quantum system that will be inside a box that is called the evident captiva. But there will be also more specific quantum algorithms, most relying on other types of physics, such as Perceval from Quandela that will be handling photonics, but also Pulsar from Pascal that will be handling neutral atom computing. Then afterward, we also bought a Pascal machine through a project called HPCQS. So this project aims to install two neutral atom quantum computer, one at the TGCC and one in Germany. And this computer should be available by the end of October, we hope. And it's called Ruby because it's a Ruby geometry based. Next, what we did was to buy a Quandela photonic system that is called Lucy, and it has been also bought conjointly with the EuroHPC, and it will probably be available, most likely be available by the first quarter of 2026. In parallel of this installation, we also got access to a remote quantum computer from Quandela in the cloud that is currently available, and that's what Samuel will talk about. So around this quantum platform, you can just make the next slide. Thank you very much. We will also try to give some services. So the first one will be trainings that will help people to understand what quantum computing is and what hybrid quantum computation with supercomputing is. We will also have a high-level support team that will help people to develop their use cases and to help people to port their code to this hybrid platform. And we also launched a project last year that is called Houses of Quantum, that is trying to bring these different services on a more local scale through the local ecosystems, the local HPC and quantum ecosystems. So that's it for the quantum platform. Now I think, Samuel, you will present what's really inside the Quandela system, a photonic quantum computer.
Yes, thanks a lot, Felix. So now you've heard that there will be a photonic quantum computer installed at the data center at TGCC. And I just want to give you a bit of an idea of what's really happening inside of this quantum computer, how does it look like, and what is this machine actually. So here you have two things. You have a schematic, which I will walk you through, of the architecture of the quantum computer, which will be available early 2026. And you already have a picture of the real machine. So this is the actual machine which will be installed at TGCC. This one is taken in our labs in Massy at our production facilities, and it will be shipped soon. So first of all, we have to understand this quantum computer is a photonic quantum computer, and that means it uses single photons to do computation. And this is really the core of the photonic quantum computer from Quandela. It's the production and the creation of these single photons. And therefore, we have here a single photon source. So this single photon source is at the heart of the Quandela technology and comes with the quantum computer and then generates a stream of single photons. That's a single photon source. And the stream of single photons coming out of the source here, they will get redirected and parallelized by something called a demultiplexer, so that we can enter multiple photons simultaneously inside the photonic integrated chip. And in this specific case, there will be 12 of these photons being able to enter the chip at the same time. And the chip has a size of 24 optical modes, which means there are 24 input and output ports of this optical chip. And this basically gives the size of the computation you can design on this chip. On this chip, you can see it here. There's a mesh of a regular structure, which has two components. One is a beam splitter, and the other one is a programmable phase shifter. And there are in total 576 of these programmable phase shifters, which can be controlled and change the value. And this is where, on the hardware level, the computation and the programming happens. But you will see in the later, when you use the machine, you don't have to tag them one by one. There is some abstraction happening in between, which makes the use of this machine much easier than having to understand exactly the hardware layout.
I think we have a question.
Yes.
From the audience.
Please.
So
are the photons coming from the DMX are integrated or not?
Yes. So the photons are not entangled. or when they leave the DMX and enter the photonic chip. But inside the photonic chip, depending on what kind of circuit one is programming and what type of detection one is enforcing, one can create entanglement through this chip. In later generations of this architecture, there will be also photons coming from the source already being entangled. And so this will be in an upgraded version of this machine, this will be the case. But in this case, the entanglement happens inside of the photonic chip. Okay, so now we know what happens inside the chip, or at least to some degree. And then the photons are leaving the chip, again, out of the 24 possible output ports. And we have detectors. So we have in total 24 of these detectors checking how many photons, or if there was a photon at each of these output ports. It's important to mention here, these are threshold detectors. So each of these detectors, they can check if there's a photon or not. But if there were multiple photons, these detectors do not make this differentiation. This is something which will come also in later generations. But in this specific machine, it uses threshold detectors. And then you can see after the detectors, everything else is post-processing, where the results of the detectors get analyzed automatically to basically generate and understand what was the output sample of this circuit, and then get sent towards the internal computer blade of the quantum computer, from which the API connection to the Quandela Cloud, or later to the internal system of TGCC, is realized, and the user can basically interact with the machine. So this is the overall architecture of the quantum computer. And yeah, we have another question.
How can you operate qubits on big 24?
Yes, so this is a good question. So we will, in the next webinar, we will go very much into detail of the algorithms and what it means to build these algorithms, but I can give you a quick glimpse to this. So in using a photonic quantum computer, if you want to encode qubits, as you are familiar with from other quantum computing platforms, you can do this via something called dual rail encoding, where you take two optical fibers, so two of these input or output ports, and one photon, and just on the spatial position of that photon, so if the photon is in the top of these modes or in the bottom of these modes, you have the two qubit states of state 0 or state 1, and therefore this gives you one qubit. So in this encoding, if you have 12 photons and 24 of these optical modes, you have 12 qubits in this machine. That's why we have this like the double number of optical modes compared to the photons. And you will see that in the next tutorial when we talk about quantum machine learning algorithms, that there's also a way of using these machines without needing this qubit encoding, and one can make directly use of the photonic nature to run algorithms. But this is just a teaser for in 2 weeks.
And I think it's connected to the second question. Is it analog or digital mode?
Yes, so this is a digital quantum computer. This is not an analog quantum computer. This is, yeah.
And we also have questions about the rate and the frequency. What is the shock rate? Is there a unique single photon source?
Okay, yeah. So first of all, yes, there's a unique single photon source, which is used to generate all the photons. And then they are getting split into the 12 simultaneous branches by the demultiplexer, but all the photons came out of the same source in this quantum computer. And the clock rate comes from how often does the laser, which we have here, excite the single photon source, which then emits a single photon. And the clock rate of this laser is 80 megahertz. So that means 80 million times per second a photon is created. And then if we translate that into what that does mean for the usability and the sample rate, that there basically come a few factors in where, of course, you have to first split it, and then you have to pass through the circuit, and then you have to detect them. And at each of these points, there's a chance that some of these photons get lost, either because they were not emitted as they were supposed to, or they were lost due to interacting with the environment, like in traveling through the optical cable, or they were not detected because of detector inefficiencies. And so out of these 80 million photons per second, some will be lost. And depending on the overall system transmittance, this will be basically determine the shot rate and also of the number of photons you're using. If you want to use really all 12 photons at once, you have a lower shot rate than if you say, okay, I use the same machine, but only use 10 of these photons, then you will have a higher overall 10 photon coincidence rate, and which translate into the shot rate. And the transmittance values will be available, and I'll show you in a second in our tutorial how you can then check what the transmittance value is live, because it sometimes varies a bit, and there's also maintenance and calibration which happens regular and on these machines. So you can always check live what is the current transmittance value, so that you know what you're dealing with. Yeah. Perfect. Okay, so I hope this gives you like an idea of what machine we are looking at. And I will now pass back to Felix to explain a bit of how you can request access, and then I come back and show you how you can actually use the machine, and we go from there.
So thank you, Samuel, for this presentation. That was very clear. Maybe I can go to the next one. I wanted to make a quick walkthrough of how to get access on the EDI platform and of the hybrid platform, and how to get access also to the cloud system from Quandela. And what we inspire from was the usual HPC access that we give to our users. So I don't know if a lot of you are familiar with this type of usage, but that's where we started from. And to start from this, we have a website that is used to get access to the HPC systems that will be reused here for the quantum platform, as we call it, and that is called eDARI. So it's the DARI for this request. And as we think that it's more exploratory system that we are installing, more exploratory system that we are installing, we think that we will give access through something that we call a regular dynamical access that will give you 100 hours of usage for the quantum system, but also from some small HPC resources. Yes. And to make a quick walkthrough of how to request resources and to create an account on the quantum HPC hybrid platform, we will start by the creation of a eDARI account on the website. So this is pretty straightforward. You just need to give your business mail address and a password. It's the usual creation of an account on the website. But from there, you can actually request some hours on the quantum platform through what we call a dynamical access. And here it becomes a bit more complicated, because you will need to give us some information about what you will do with our system. Because as Sabine mentioned earlier, but these systems are accessible free of charges, but we have to ensure that you will use them for open research, so for publicable research, basically. So that's why we need to have some information about what you will do on these systems. Also, some information about the institute you are coming from. So, for example, if you are coming up from a public research institute, you will need the name, the team, the people, and what you are doing there. We also need, if you come from a private institute and you are doing open research, the SIRET number, so it's the French identification ID number for your company. And after giving us all this information, we will also need a visa that will that will basically sign by your supervisor that will ensure us that all the information that you gave us are actually true. From there, we have an internal validation process that is a request to the director of the TGCC that will ensure that the project is scientifically viable and that what you will do is actually something that can be done on the system. And this takes basically 2 to 3 days. And from there, you already can access the Quandela Cloud in remote, because we will give you a token to use them, to use the system, and that Samuel will explain how to do it just afterward. But if you want to access the full quantum platform, then you also need a TGCC account. So you have to make a request for a creation of a TGCC account. And there, you need to give back some information, because this is handled by the TGCC, not by our teams. So the name, the CRET number, if it's a private institution, and so on. But you also need to give the connection information. So what IP address you will use, and the fully qualified domain name that is associated to this IP address. And finally, you will also need a visa that ensure that all the security conditions as encountered, that will be signed by your manager and the security officer of your company, of your public institution. Then from then we will have a security investigation to ensure that what you will do on our system is not completely out of the line. This can take up to 2 to 3 weeks, depending on the information that you gave. And from then, you can access the Joliot-Curie Quantum platform through an SSH login. So you will have to connect through the terminal, send the codes that you want to run on the platform, and then run them through this SSH connection. So that's it for the walkthrough. I don't know if there is any question.
I think there's a question on the availability of the access to the Quandela system. So there is already, you can already request access to the remote systems through the Quandela Cloud. And the Lucy system will be available early 2026.
Exactly. Thank you very much. And that was the only question, or?
I think everything was so clear.
Thank you very much. Is it possible to have access to it as a freelance? Well, I think yes, but we have to ensure that what you will do on the system is open research. So you will have to at some point publish some result that you get on the system in research journals, or on an archive paper, or something that proves that what you do is open research.
So the other question is, can we also request access to Pascal Ruby system?
Yeah, maybe it wasn't super clear, I think, when I presented it, but when you will request some resources, you will request access to the quantum, what we call a quantum platform, which gives you access to our quantum system. So Ruby is part of it. So you will have access to the Ruby system, but also to the other quantum computers that we will install at some point. So Lucy is getting installed at the moment. It will be delivered by October, by the end of October, and it's supposed to be available by the first quarter of 2026. But we are also planning some next installation of different complementary technologies, and this will happen in the future. But with this access, you will also have access to these new systems.
And maybe to just to complement this is all in this part here of accessing the TGCC platform. The cloud platform, which is available right now, this is specific to Quandela. This, if you want to access a quantum computer today, then you have to go via this cloud, and you can only access the one of Quandela, or you wait until either the one from Pascal or the one from Quandela or the next one will be available through the TGCC platform.
Thank you very much for this precision. So I think if that's okay for everybody, maybe we can continue, because Samuel, you wanted to present how to access what is already available, so this remote access to the Quandela Cloud, and I think it's super interesting to have a presentation of it. So go on.
Great, thank you. So exactly as Félix said, right now I want to show you not what's available in the future, but what's available today. So this means how you can access the quantum computer from Quandela today, which is not the one which will be installed at TGCC, but it's via the cloud, and you still can request access through the process with IDARI, as Felix just presented, and you will be allocated credits free of charge as long as you submit a project supporting open research. Once your project basically got accepted and you have been allocated some credits from GENCI for your project, what you have to do is you now have to go to the Quandela platform, which is the Quandela hub at hub.quandela.com. I will show you in a second how this looks. Sign up to this, create an account there, and then you can go to the Quandela Cloud, which is inside of the Quandela hub, and create a token. And then with this token, you can directly connect to your script of your job, which you want to submit to the quantum computer, and send it via the Quandela Cloud to the quantum computer. And it will be very similar once you access the quantum computer available at TGC. The only difference will be that you don't go via the Quandela Cloud, but you will go directly through the TGG system. So you do not need a token, but the script, which I will show you in a second, of programming on the quantum computer using Perceval, which is the Python library, which basically allows you to create photonic circuits and create photonic algorithms. This will be the same what you would do right now, or what you will do on the through the TGCC platform. So there's a lot what we will talk about today, which will be exactly the same also for the Lucy machine. Any questions before I jump into the tutorial and show you exactly how these platforms work and how we can submit an actual job to the quantum computer? No?
Yeah, well, I think there was maybe a misspelling on the address. I think it's hub.quandela.com.
Yes,
No
I'm very sorry. I will change that before I send the slides to you.
And do you have any details about the fee for using Quandela Cloud?
Yes, so as Felix mentioned, this will be again free of charge. So you can access the Quandela Cloud for free by submitting a project proposal with IDARI and then get credits allocated to you. So again, you don't have to pay since this is a public organization and you're doing open research.
So that is if you're doing open research. If you want to do private research and just keep the results to yourself, then I think you can also directly connect to the Quandela Cloud and then have some...
Yes. If you do not want to go via the IDARI process, you can connect directly to the Quandela Cloud and you can just buy as many credits as you need for your project, and you can see the prices on our website. I will not go into that now because that's not the topic of today, but that's also possible.
And is this access temporary in waiting for Lucy?
Yes, this is indeed the case. So this cloud access via which you can access through the IDARI project and getting credits through GENCI will only be available until the Lucy machine is available for you via the TGCC system. Okay, cool.
No, there is just one that appeared. So what are the favored use cases for using the system?
Yeah, very good question. So this will be the topic of next webinar. So I don't want to take anything away, but generally speaking, there are different types of use cases, some surrounding quantum machine learning in different aspects, some surrounding optimization tasks, and some surrounding simulating of chemical processes. And we will look at some of these, not all, because in the next webinar.
So I can take this one. So there was a question that was asking if there was a special resource line for Quandela Cloud / Lucy. No, there is not. So when you request for resources on this platform config, so the way we call it, we will grant you credit for the Quandela Cloud so that you will be able to use the Quandela Cloud and also the Lucy machine when it will be available.
So basically the first 3 steps here, they will be exactly the same, no matter if you go to the Quandela Cloud or if you continue to the TGC system.
And if you already have an account with access to the Quantum platform, you should have received a token that granting you access to these Quandela Cloud resources. I think.
And if you have not,
then you have to reach to us because I think it's not.
I think you can reach us through access@genci.fr. I'll just write it.
Perfect. Okay. If there's more questions, we obviously have time in the end also. But now I will jump and show you actually how we physically access the quantum computer today and actually run our first job live on the quantum computer to see that it actually works. So I'm gonna switch to a Google Colab so that you can easily recreate it. And I will import a new notebook, or it's the same as we see already, but I just want to show the process. So we go and import here a new notebook. This one I will share also with you, so you will have access to this notebook. And the first step we have to do is we have to install Perceval, the Perceval library.
Can you just zoom in for a bit if it's possible?
Yes, it is. So now I think it should be easier to see. So the first thing we have to do is install the Perceval library. So either you do it here in the notebook or you do it in your normal code editor. Oh, there we go. And this will take like a few seconds. So while we wait, we just go to the Quandela Hub. So this is the Quandela Hub. This is how it looks if you go to this website. You can see already I'm already logged in. Otherwise, there will be a login button at the top. If you don't have an account already, you create an account, and then you log in. So that's very straightforward. And then you go to the Quandela Cloud. Is there a question?
Yes, there's a question. So if the eDiary project is shared by different people, will everyone receive a token or just the project manager? And in the latter case, can several people use the same token?
Yes. So I will address this question when I show you the process. So there's definitely a solution to this this scenario. So once we go to the Quandela Cloud, we can then go to our dashboard where we have an overview of all the machines available, which are some of these quantum computers and some of these simulators of quantum computers or even GPU simulators, which will be accessible to you with your credits. And you will see your current credits on the top right. So you see in my case, in this account, I have still 60 credits available. And this is what you will receive from TGCC. So we just need to make sure we are clear on the naming. You receive credits from the TGCC for your project, and then you can create a token to connect to your code to the platform, which I will show you. So the thing you receive, what we talked so far, is credits, and these ones will be assigned each to a personal account. But if you are multiple people, you can of course have each of you have some an account, and each of you can receive some credits, and you can basically share them between you, and also move them from one person to the other, depending on who needs these credits. Now you can create a token. So you go here on the left side on token, and you can create a new token, or in my case, I created one already for today, and I can copy the token, and we will see in a second how we're going to use it. Now, if you're now working on a project together, there's two options. Either, as I said, you all create one account and you all create your own token and you just share the credits in between us, in between you, or you decide we just let one person create an account, they get all the credits, and they create one token, and then they will just share the token with the other people. Depending on the project, one makes more sense than the other, but of course, if you only use one token and share that, there's little way for you to know who used which credits, and who used the token for what, because it's all done with the same token. So depending on what you need in the project and how many people you are, one or the other might be more useful. Okay, so now we have created a token, and we can go back to our notebook, and we see we have installed Perceval. Perfect. Now we can check if we have the current version. And the current version is Perceval 1.01. And we see, very good, we have the up-to-date version, of course, since we just installed it. And now we can start by creating our first quantum algorithm, or in this case, a very simplified quantum circuit. The quantum algorithm, as I said, I will talk about in the next webinar. Now I really just want to show you how you can run the most simple job on the cloud, on the quantum computer. So what do we do? First, let's do a simulation of that and then run it on the quantum computer. So we first understand what we're actually doing. Initially, we have to define an input state. And with input state, I mean where and how many photons do we want to insert into the chip. So basically everything in Perceval, what we're doing is, if we look back to the architecture of the quantum computer, is concerned with the photonic integrated chip. We decide what goes in the chip, and we decide what happens inside the chip, and then we measure what comes out of the chip. So the first thing is, we say, actually for this example, I only want to use 2 photons and put them in 2 different optical modes. So I only use 2 photons and 2 modes. This is, of course, not making use of all the 24 optical modes and 12 photons available at Lucy, but it's completely valid. And the quantum computer takes care that if you don't want to use everything, that it adjusts the needed hardware adjustments for that. Second thing is, we can create our circuit. Which circuit? I mean, we create what happens on the chip. Physically, it means which phase shifters get what value, but for you do not have to worry about that. You just build your own photonic chip, and you can even build a very simple one, in this case consisting of only one beam splitter. BS stands for beam splitter here. So we create a very, very simple circuit where we have only one beam splitter, and in the background on the quantum computer, all the different phase shifters will be adjusted so that effectively it is just one beam splitter. So you don't have to worry about that. You just create your circuit. Next thing is, you could simulate some noise. We'll not do that right now, but just so you know, you have the possibility to also simulate noise if you want to. But since we want to run on the real machine, we'll just take the noise of the actual quantum computer. And then we have to create an experiment. So this is basically just a wrapper of all the different input parameters. Right now, it looks a bit empty. It just contains the circuit, but you will need this structure also to access the TGCC system, where then there will be some other parameters. So that's why it's very important to use this experiment class. Once you have created your experiment, you can start either running it on the quantum computer or simulating it. So here we are just creating a processor and telling the processor what is the backend to simulate it. Here, SLOS is the most common backend to run a perfect simulation of the quantum computer, and is very doable for a small experiment as we do today, where we only use 2 photons. So we have defined what we want. We say how many photons we want to detect at minimum. We can play around with these numbers. You don't have to worry about that for now. You can test it out. But it's just making sure that basically what we want to get out. This becomes relevant when we have system noise. And then we tell the processor that we have an input state. Now comes what we want to get out of this experiment. So we have to define how many samples do we want to generate. So if we think about the quantum computer, how often do we want to send 2 photons into the chip and then measure where these 2 photons ended up? And in this case, we say we want to have 200,000 of these samples. You can, again, depending on what you want to do, change that, of course. And then we use an object called the sampler to generate these samples. So again, in this first block here, this is completely a simulation on my computer just to test if everything works and we understand what we're doing. And then I will show you in the next step how this can be translated very easily onto the quantum computer. So let's run this. And then I think there are some questions.
Yes, there are. So is the measurement destructive, like the case of neutral atom?
So it's destructive in the sense that the photons which enter the chip and then get measured, they will disappear. So yes, but basically the way the quantum computer works is that the photon source, as we saw, it's continuously generating 80 million photons per second. And basically, every time we want to have a sample, we just take new photons of these. So the photons we measure, they are destructive, but there's continuously coming more photons our way. So this is not really a problem. So there's a difference to the neutral atoms where there needs to be like some reconfiguration happening in between, which does not happen here.
And there's another question on the role of the optical elements. I imagine the phase shifters are kind of entangling gates. Can I think of them as controlled phase shift gates?
Not quite. So the phase shifters, they are the programmable parts, but they are not the parts which bring the entangling aspects, because the phase shifter only acts on a single photon. And the beam splitters are really the components which bring the quantum effects of superposition and interference, where because they act on specifically on two of these optical modes, and therefore basically creating this superposition of photons arriving from either part. And the entanglement comes then from like the combination of all of this and on the detection of and a post-selection of certain samples.
Okay, and then there are questions on the properties of the machines, like the error rates, fidelities, and a question on whether or not decoherence for photonic quantum computing is a problem, and if you are working on error correction.
Yes, so let me take them one by one. So I'll get back to the different error sources and the basically the fidelities of the different tasks. We have basically some benchmarking, and there are more benchmarking basically happening continuously, and you can do your own benchmarking on these fidelities. This could be like a very good first test of using the machines for yourself to basically get a feel of how it works. Coming back to the decoherence. So photons do not decohere. So this is a big advantage. The photons do not decohere in the sense that they lose the quantum information. So there's no decoherence on the photon level. But as I mentioned before, there's something else, which is called photon loss. And this is really the main challenge using photonic quantum computers, that the photons get lost on the way. And basically, the higher the full transmittance of the system, the less of a problem that is. But this is something which basically you can always compensate by just generating more photons. Then it would just take obviously longer, and depending on how many photons you want and how many photons get lost, this might at some point be not practical, and therefore we need to have certain levels of transmittance, but there's no decoherence in that sense. And now the last point was if we work on error correction. Yes, we do. And we already have published a full architecture of the full tolerant quantum computing platform using the photonic aspect. And you will see if you go and look into this architecture, I can share the link of the paper, that we are using exactly the same components as we use today, but we use some extra components. So we will not just use a single photon source, we use multiple photon sources, and we use different types of chips, and we use some elements of where we have like adaptive measurements. And all of these components, they will also be added to our current machines step by step by like each generation or in like upgrades of the machines. So the path to a fault tolerant error corrected machine is really what we are going along. And this machine, what you are using right now, or you will able to use, is really like a milestone along that path.
Thank you. There's another question. Do you have any PD solvers on the primitives of the quantum toolbox?
Yes. So you're mentioning the quantum toolbox, which is a feature on the cloud. If we just go here, you can see that here. And here we have 5 different primitive algorithms. Here we do not have a differential equation solver specifically, but there's 2 basically options. One is you can look at our documentation of how differential equation solvers can be implemented in our current architecture and then program it yourself. Or you can use one of these like the VQE, the variational quantum eigensolver algorithms for certain differential equation solvers where you basically translate it to a energy ground state problem. So these are 2 options, and we might add other primitives to this toolbox as we go along. But for now, there's no specific differential equation solver there.
Okay, another question on the specifics of quantum photonics. Is there a crosstalk?
So when we talk about crosstalk, we if we look in our chip, I guess we talk about how the photons in one optical mode affect the photons in the other ones, and that does exist. And specifically, it exists not on the photon level, but exists on the phase shifter level. So the way we basically manipulate each of these phase shifters is by applying some heat physically to them, or like a voltage which then translates to heat. And that has some crosstalk. Of course, if I apply some heat in one location, it's not gonna just like get blocked 100% and stay in that location. There is some crosstalk. And to basically overcome that, or to minimize the effects of that, we have inside the quantum computer a machine learning algorithm which basically adjusts and learns how to apply the right amount of voltages to get the close to perfect fidelity of the circuit which we actually wanted to implement. So basically, crosstalk is not something which really affects you as a user and is basically taken care of under the hood from the machine itself.
Okay, can we simulate a short program of Perceval algorithm in a local machine before sending it to the quantum computer?
Yes, that's what we just did. So that's a great transition back to where we were. So we've just simulated on my local machine this little program where we send 2 photons into the machine and simulated what happens if they pass through a beam splitter. And what we can see is we see 2 photons entering, 1 in each mode, and we see the output samples are 2 photons in the top mode or 2 photons at the bottom mode, and we see how often this happens, and we also see what the probabilities of each of these were. Now, this is a local simulation, and if you remember, in the actual machine, we only have threshold detectors, which means they would not be able to detect that there were 2 photons, but they would register this as there is at least 1 photon. So the output of the quantum computer would be 1, 0 and 0, 1 instead. So this is something we need to take into account and to when we basically design our algorithms. Of course, we can also simulate that in the simulation, but this is not what we've done here.
Okay, and there's a request to share some references about the work from Quandela.
Yeah, we can do that. No problem. That's that we will do that. We send you some references afterwards. Okay, so now let's go and do the same experiment as we've done here, but on the real quantum computer. And we have a few more minutes, so we'll do that, and you'll see it's very easy. So the first thing is we have to take our token and insert it here so that the machine actually knows, or our script knows, that we are connected and we have access. So I've insert the token which I just created, and I can run the script to save it, and now the whole script knows that we have this token. And now if I want to run our experiment, what we just created before, on the quantum computer, very simple, similar as what we did before, I create a, this time, remote processor. So now it's not longer locally simulated. And I detail what platform we want to use. So if we go back to the cloud, we have a list of platforms we have access to. And we can see there's 2 QPUs. If QPU is in front, this is a quantum computer, and there are some simulators where we have sim in front of it. And we can see right now the QPU Ascella is available and the QPU Belenos is not. So I'm going to use the QPU Ascella, but when you try it, the QPU Belenos might also be available. So you can do both, or you run it on like a simulator, maybe it's one which is more powerful than your own computer. But so let's go back. We have QPU Ascella, and then we just add our experiment, which is our circuit from above. And here we just tell it to add it at the beginning. That's why we say 0. And then same as before, we have our input state, and we say we want to detect at least 1 photon, because now we have to keep in mind the QPU Ascella, it's not perfect. It has some noise, and specifically it has some photon loss. So we will sometimes lose a photon, and sometimes we will not lose a photon. And of course, sometimes we could also lose both photons, and then we would just not detect anything. And this is not really interesting for me to see, because it doesn't give me any information. So I said, I only want to see the results where we at least detected 1 photon. And I want to get the number of samples, as we had before, of at least 1 photon being detected. And now we just, again, create a sampler. And here we create now a job. We give it a name. And we now can run this, which will create a job on the Quandela Cloud. And we will see the idea of the job printed next to it. So this is now our job ID. And if we go back to the cloud, to our subsection jobs, we will see exactly this ID. And this job has just been created. And we see it's been created on the Quandela QPU Ascella, and it's currently waiting. So this means the job has been created, and now maybe someone else is using the machine. So we have to wait until it's our turn. And once it's our turn, the job will be executed on the quantum computer and then returned to us. The job, since it's a very simple job, which we have just created, will not take a long time. But if there's someone else in front of us, of course, we might have to wait a few minutes, depending on that. There's a question.
There are several. So one of them is about the role of the beam splitters.
Okay, so again, the beam splitter is one of the 2 components, and they are the ones which act on 2 optical modes, which allow basically a superposition of the photon in multiple optical modes, and which therefore give rise to quantum interference. And in this example, I'm just using one beam splitter just as a simple example. But of course, normally you would have like a bit more complicated circuit with beam splitters and phase shifters. And the combination of these allow you to create any unitary transformation of the incoming photons to the outcoming photons.
How many available qubits are there by Quandela Cloud?
Good question. So on the Quandela Cloud, we have, as I showed you, 2 quantum computers available. One is the quantum computer Ascella, and the other one is the quantum computer Belenos, which currently is not available. That's why we're using Ascella. Ascella has half of what is available for Lucy, so 6 qubits. That means 6 photons in 12 optical modes. And Belenos has the same as Lucy, meaning 12 qubits, 12 photons in 12 optical modes.
Thank you. Will we have natives like neural net transformers?
Yes, and we will talk about that in the next webinar.
Stay tuned. What is the main bottleneck of quantum devices currently? Is it photon loss due to limited transmittance of the system or something else?
No, it's very correct. Photon loss is the main bottleneck.
Okay. And from your point of view, how can artificial intelligence researchers profit from this opportunity in order to explore hybrid approaches combining quantum photonics and AI?
I'm very happy about this question because this is something which we will very much in detail explore in the next webinar, where we'll introduce you to a second Python library called Merlin, which we have launched this year, which does exactly this. It takes the general and the known AI and machine learning architecture, in our case PyTorch, and integrates it with the photonic neural nets, which we will discuss in 2 weeks, and allows AI researchers, without needing to learn how the exact hardware of the photonic system works, to build hybrid quantum AI models and test them and see basically what combination works best. So stay tuned for that.
And going back on the matrix transmittance, how many photon loss should I expect?
I will show you in a second. So let me now continue in our process. So we've now launched our job. Let's now see what the progress of our job is. And we see the job is already completed. So if we go back to our cloud portal, we see the job is completed. So this, as I said, was very fast. We can see the job only took a few seconds. And most of that was not the generation of the photons, but the sending it to the cloud and setting everything up, because we only had a very short circuit of 200 samples. And now if we go and we want to retrieve the results, we can do this directly here in our script. And here we have our results. And you can see they are slightly different to what we did in simulation. The first difference is that we don't have 0, 2 or 2, 0. This is due to the threshold detectors. So this is exactly what we expect. But we also have sometimes the case of 1, 1, which was not the case before. And I will not explain you exactly where it comes from, but it comes from another error, which you can explore. And then you can also use, get the results of any job you've ever run. We don't have to go into this right now. And I just want to come back to the last question to see what is the expected photon loss currently. And you can check that for whatever machine you use. So what you can do is you can have your quantum computer and print the performance of this specific quantum computer. So let me do this. So this is then the live transmittance or the different loss parameters. And we can see, first of all, here we have our 80 megahertz clock rate, which I mentioned before. Then we have something which is called the Hom percentage. I've not explained, and I will not do it today, but you can learn about it yourself or ask another time. And we have here the transmittance. And today we have a transmittance of 3% in our machine, which we just used. This is, of course, very low in compared to 100% optimal transmittance. And I can tell you this will go up substantially as we go along, and the machine Lucy will have a higher transmittance than this. But this is, as I said, this is the bottleneck. So this is the main thing our engineers are working on. And this is what we have. And then we have another error, again, which I will not go into right now. And now we are also out of time. So if there are any final questions, maybe we have
There is one about the dual rail encoding. Why is there twice more optical modes than photons? Is it mandatory?
Yes, so this is just the basically the setup of the architecture. So if we go back to our of the architecture of our circuit. This is just the size of the photonic circuit which we have decided to put in the machine. This does not mean you have to use all of these optical modes and all of these photons, but it's what's available to you. And the numbers come from the dual rail encoding, where you have one photon and two optical modes together equaling one physical qubit. And that's why we have these numbers.
Okay, should we then have some final words?
Yes.
Is it okay?
Yeah.
Okay, so thanks a lot for this insightful presentations, Félix and Samuel. So now we do hope you will all be able to request access to the Quandela Cloud via the eDALI platform. Should you encounter any trouble in doing it, don't hesitate to reach out to either Félix or myself, or to reach out to us through the access@genci.fr address that was provided in the chat. So the slides and the recording of this webinar will be shared later on through the HQI website, and we'll be also sharing it on social networks. There will be a next webinar, as touched by Samuel, on the 14th of October from 2 p.m. to 3 p.m. So don't miss this one. In this second webinar, Samuel here will show you how to prepare your first quantum machine learning algorithm using Perceval and Merlin and Quandela's environments. The Eventbrite link will be shared online very soon, so stay tuned. And don't hesitate to follow the LinkedIn accounts of HQI Program, GENCI, CEA, and Quandela to get this information on time. Thank you very much.